All right, we're going to move into the discussion of half-life in chemistry. So half-life is a term you may have heard, especially in the discussion of radioactivity. Half-life can be defined as the time necessary for a reactant to reach 1/2 of its initial concentration. All right, so the first thing I remember when I heard this definition is like, why half-life, right? Why not full life or something like that? And I'll explain this graphically why half-life is very important. All right, so let's go ahead and take a look at a plot of the concentration of A versus T. And we're going to consider this to be a non-zeroth order reaction. That's just terrible. Sorry, let's move that. And if the reaction is not zeroth order, most of our plots look like this. All right. So if we tried to figure out this was the full concentration up here, and this is kind of where it almost ran into zero down here, but it really didn't, right? You know, where did it fall half of its original concentration? So you can kind of estimate this, right, that it might be somewhere around here, okay? It fell in half. So if we had a number here, this would be 5, and down here would be 0. Half of 5, of course, is 2.5, all right? So why is the half-life important? Well, look what happens in the first part of that curve. It falls very, very quickly. All right, and then it goes really, really slow after that. All right, so the half-life is really the very, very beginning of the reaction, and it tells you, or it takes place over the beginning of the reaction. It really tells you how long it's going to take for that concentration to fall in half. All right, so it's a useful number because it's really telling us that biggest chunk of the concentration is going to happen in the first half-life. All right. So we can actually plot this a little neater, all right? So if we had 10 here, and then 5 here, 2.5 here, and then 1.25 here, all right? So what I can do is I can try my best to draw a curve, all right? And at 5, we would call that T1/2, all right? Because that is the time. Of course, my axis, is the concentration of A versus T. All right. So there's my first half-life. I can actually extend out here, and this would be my second half-life. I'll put parentheses 2 there. All right. And then as it falls to 1.25, that is my third half-life. Of course, you can go on and on and on because your concentration, if the reaction is reversible, should never actually reach 0. All right, so you have several half-lives. The first half-life is going from 10 to 5. The second half-life is going from 5 to 2.5. And then the third half-life is going from 1 to 2.5. All right, so the half-lives are very dependent upon the order of reaction. All right, so why don't we go ahead and look at a first-order reaction. And what we're going to do is we're going to write the integrated rate law for it. So the ln of A at time t is equal to minus kt plus the ln of A0. And these should be n's. My little pen is acting up. Pardon me. Why don't I just completely get rid of that because it looks terrible. Apologize. So it's the ln of the concentration of A equals minus kt, the ln of A0. So that's our integrated first order rate law. All right. So we can actually state something that at the half-life, the concentration at time t is equal to 1/2 the concentration of A0. All right, that's the definition of the half-life. All right, our concentration, AT, has fallen to 1/2 of the original concentration. All right, so we can plug in our new AT value into that first order integrated rate law. So the ln of 1/2 A0 is equal to minus KT plus the ln of A0. All right. So I'm going to move the ln of A0 to the left-hand side of the equation. So to do that, I'm going to subtract this term from both sides, and I'll rewrite that over here. So we have the ln of 1/2 A0 minus the ln of A0 equals minus KT. And we can take advantage of the natural logs that when they are subtracted, we can write them as a quotient. All right, so our expression will look like this, and our A0s will actually cancel out. All right, so then we have the ln of 1/2 equals minus KT, and the ln of 1/2 is a constant. All right, you can actually just take ln of 0.5 on your calculator, and it comes out to be negative 0.693. And then I can divide both sides by minus k. So when I do that, my expression then changes to that. And I'm going to go ahead and put T1/2 there to specify I'm talking about the half-life, or the time half-life. All right. So this is the half-life expression for a first-order reaction. And if you look at it, all right, it's not dependent upon the concentrations, right? What I mean by that is, what is it dependent upon? What is the half-life dependent upon? Well, you have a constant of 0.693 here, but it's dependent upon the rate constant, all right? So that means we can look at the half-life here, plot for a first-order equation, and if I put the concentration of A here and the concentration of T, then I have an initial concentration of 10, and then I have a concentration of 5, and then 2.5, and then 1.25. These times should space out very nicely. All right, let's just say that it takes 100 seconds to get here. All right, so it takes 100 seconds for it to fall in half. Now, since the half-life of a first-order reaction is only dependent upon the rate constant, well, for it to fall in half again is 200 seconds, and for it to fall in half again is 300 seconds. That's pretty cool for a first-order rate equation, all right? So it doesn't depend upon the concentration, all right? 0th order and second order, they will be concentration dependent. The first order will not be. So that allows us to do something pretty cool called radiocarbon dating that we'll talk about here in a minute. But let's just see this equation kind of being used in an example. So we can actually have the dissociation of iodine into iodide. All right, so we can take I2, and it can dissociate into 2 ions of iodide. And this process is first order and has a rate constant equal to 0.271 inverse seconds. All right, and again, the units of inverse seconds, or s to the minus 1, is telling me that it is indeed first order. All right, so the question is, what is the half-life for this process? And notice I don't need the concentration, right? Remember, half-life is only dependent upon the rate constant if you're dealing with the first order reaction. So for first order, oops, 0.693 K equals T1/2. All right. So we're solving for the half-life. All we got to do is simply plug in 0.271 seconds, or inverse seconds there. And that's going to be equal to 2.56 seconds. All right. So what have we answered? Well, it takes 2.56 seconds for the original concentration of I2 to fall in half. All right. What would it take for the original concentration of the I2 to fall by a quarter? All right. Well, let's think about what that means. If I have 1 going to 0.5, that's the half-life. If I go 0.5 to 0.25, that's a quarter. How many half-lives does that take? It took 2 half-lives, right? So if it took 2 half-lives, well, it's just simply 2 times 2.56 seconds, and that's going to be equal to 5.12 seconds. All right. And of course, if it fell to 1/8, that would take a third half-life. All right. So when you're dealing with first order equations, don't overthink it, right? It's very, very simple. All right. Okay. I talked about radiocarbon dating a minute ago, and what's cool about the first order equation half-life is that a lot of radioactive decay processes happen via first order kinetics. All right, and one such decay process is when nitrogen in the atmosphere is hit by neutrons in the upper atmosphere. Right, there's a lot of high energy particles up there in the upper atmosphere. So if we take a neutron, all right, so it might have been a while since you've seen this notation, but I've got the chemical symbol capital N for nitrogen. It has a mass number 14 for this particular isotope and a atomic number of 7. All right, a neutron, okay, has a mass number of 1 and a what we call atomic number of 0. It means it has no protons. All right, obviously a neutron is not a proton. All right, so when we have this nuclear reaction that happens, we just simply add to get to 14 carbon 14 plus a proton, all right, or a hydrogen nucleus. Okay, so this is a process that happens in the upper atmosphere. We'll talk about nuclear chemistry later on in the semester, but nonetheless, upper atmosphere, we have a reaction of atmospheric nitrogen reacts to give us a carbon-14 isotope. All right. Almost all carbon in nature is either carbon-12 or carbon-13. There is a teeny amount of carbon-14 that is produced through this process. And it actually makes it up the food chain, believe it or not. All right, so plants absorb this carbon-14, and then people eat the plants. Animals eat the plants. Any living organism is uptaking carbon-14, right? And they're taking it up very, very slowly. All right, so we say there's this constant level of carbon-14 that all living organisms are uptaking. All right, and it decays quickly back to nitrogen, and it emits an electron in the process. All right, so the thing is that is important about this is when an organism dies, it no longer uptakes this carbon-14. Therefore, the carbon-14 decay, which is happening right here, all right, this process is slowing down, all right, because you don't have as much carbon-14 to be emitting, decaying, all right. So, point of the matter, if you're alive, you are uptaking carbon-14, and it is decaying. If you are dead, you are no longer uptaking carbon-14, and you are decaying it much, much slower. All right. And this decay process of the carbon-14 going back to nitrogen-14 is first order kinetics, and it has a half-life of 5,730 years. All right, so the half-life of this decay process is 5,730 years, and it's a first order decay process. So how can we use this to date a once living organism? All right, so maybe you've heard about, like, they can radiocarbon date, papers or old documents. That's because they were made out of parchment paper, which of course came from a living organism at one point. So they can radio date that tree that was used to make that paper. All right, so let's look at an example here. Enough talking. Remains of an organism are found to have a C14, which is carbon-14, decay rate of 4.5 disintegrations per gram of carbon. All right, so disintegrations, that's of course the carbon-14 decaying to the nitrogen-14. All right. Living organisms have a decay rate. All right, if you were paying attention, should this decay rate be higher or lower, all right, than a dead organism? And the answer is it should be higher, because a living organism is uptaking carbon-14, all right? Thus having it decay. So living is 15.3 disintegrations per gram of carbon. How old are the remains? All right. When you do radiocarbon dating, there's two steps. All right. The first step is you need to find out what the rate constant is. And then the second step is you're going to use the integrated rate law to find time. All right. So let's look at this. Step one, find the rate constant. Which is, of course, K. All right. So we know our T1/2 expression for any first order decay process is 0.693 over K. All right. And since we're dealing with carbon-14, that has a known half-life. All right. And that known half-life we covered just a minute ago is 5,730 years. And we just rearrange to solve for K. And it's okay to keep it in units of year here. There's no reason you can't. So some rearranging. In algebra, I get 1.209 times 10 to the fourth inverse years. All right. So typically we were looking at rate constants having, seconds in them, but this time we're just going to keep it in years. All right. So that was step one. We just found K. Now we're going to step two, use integrated rate law to solve for T, which is the age. All right, not T1/2, but T. All right, this is the age of the organism, if you will, or the remains. Pardon me. So, integrated rate law says ln of AT is minus KT plus ln of A0. All right. And I can go ahead and move these things around. So I'm going to do ln of AT over A0 is equal to minus KT. All right. Now, remember, I'm solving for T here. All right, so I need to divide both sides by K. all right? And once I've finished with that, I'll have ln of AT over A0 times 1 over K equals T. And T is my H, all right? Pardon me, that should be negative K. Don't forget about that negative sign, all right? Okay, so we had K from step 1. Now, what the heck are these concentrations, all right? When they're in brackets, we're talking about molar concentration, all right? They gave us something, what was that? Disintegrations per gram of carbon. So does that mean we've got to convert disintegrations per gram of carbon into molarity? And the answer is no, not for a first order process. Why? Look right here. The units, no matter what they are, whether they're molar, disintegrations per second per gram per whatever, who cares? As long as the units are the same and you divide, those units cancel. All right, so that makes it very convenient. So our disintegrations were what? AT, all right? So that is what that thing is disintegrating at the moment, 4.50. What it began disintegrating at, which means when it was alive or living organisms, should be disintegrating at 15.3, all right? So we multiply that by negative 1 over, what was our rate constant we found? 10 to the minus 4th year. Inverse year, right? So calculate it, right? Simplifying that natural log, you're going to get negative 1.22 times negative 1 over 1.209 times 10 to the minus 4th inverse years equals T. And when I do that, I just simply multiply those two numbers by each other, and I find that my T is equal to 10,090.9 year. All right, so that's how you use radiocarbon dating to figure out the age of what was once an alive object. All right, so make sure you follow those two-step processes and you should have no trouble. All right, in the interest of time, we're going to move, no pun intended, away from the half-life on the 0th order and the 2nd order. All right, they're not quite as useful, and it's really just an exercise in just plugging and chugging. And I'd rather get into more interesting things than spend time talking about the 0th and 1st order half-life processes. All right, so one more place before we move on from half-life that is very interesting is in what's called pharmacokinetics. All right, so this is the study of kinetics in pharmaceuticals. All right, so a lot of drugs, knowing their half-life is extremely important. And the reason why is because that will dictate the dosage. All right, so if the half-life of the drug in your body, and what does that mean? Right, that is the time when you take the drug for that initial concentration of that therapeutic drug to fall in half. All right, so it's very important to know that number, because that concentration, if it falls very, very, very slowly or has a slow half-life, then it's going to be around in your body quite for a very long time. Therefore, you don't want to be taking that pill every 4 hours, for example. Right, if it has an extremely short half-life, then you may have to increase your dosages per day. All right, so pharmacokinetics, it's a real field and very, very important. All right, to understand kinetics and how drugs work. Okay, next thing we want to move into is the effect of temperature on reaction rate. Now, in Lab 4, the simulator, you were able to see, hopefully, that if you increased temperature, you increased rate, all right? And that really comes from what's called collision theory, all right? So collision theory, I'm going to give you a very basic idea here, is that when you take two particles they have to have what we call the right kinetic energy, and they also have to have the right alignment to actually collide to make our new particle. All right, so if we had two hydrogen atoms and they collided to make an H2 molecule, all right, there is a requirement for the kinetic energy that's required, okay, and also a requirement for their, if you want to call it, approach angle, all right, to make that neat little transition state to the H2 molecule. All right, so that can be all put together in something called the Arrhenius equation from the Swedish chemist Arrhenius. Right, and this A is what's called the pre-exponential factor. All right, and that has to do with, okay, the kinetic energy that's required. All right, it also has to do with the alignment of the particles and so forth. So we call that the pre-exponential factor. All right, and what we also see here, of course, lowercase k is the rate constant. So of course, the bigger that number, the better. We also see temperature here. All right, and of course, we have a negative sign in front of our exponent. All right, so that is telling us that the larger the temperature is going to give us a larger K, right, because of the negative. Okay. There's also something here called the activation energy barrier. Or simply just called the activation energy. And that's going to tell us the larger the activation energy barrier, the smaller K will be. Right? Remember that negative sign and that exponent is kind of flipping everything upside down on us. All right. So a larger activation energy is going to provide a smaller rate constant. Okay. So if you want a reaction to go fast, if you have a high temperature and a low activation energy, that thing is going to go quickly. And hopefully you saw that with the simulator from Lab 4. All right. So let's talk about a few things. If we increase the activation energy, our rate is going to go down. If we increase the temperature, the rate is going to go up. Right? So that's two things that we get from that Arrhenius equation. And what that can be done, or what we can do with that, is we can look at a reaction coordinate diagram. And you'll see a lot of these in organic chemistry if you move on to that course. And we have something called the reaction coordinate on the x-axis. So we have energy on the y, reaction coordinate on the x. And the reaction coordinate is some place on the potential energy surface. All right. So we can loosely say that's kind of like reaction progress. All right. As something goes, let's say, from A to P. All right. So we're going to start over here. That's kind of the traditional place to put A. It has some intrinsic energy, random energy. All right, that is, well, not random, sorry, intrinsic energy. Just based on its chemical makeup, it has a potential energy. All right, and depending on what the intrinsic energy of P is, it could be lower or it could be higher than A. All right, and that's going to dictate whether you have an exothermic or endothermic reaction. So we're not going to even draw the curve yet. So if I look here, A is higher than P. So we're losing energy as we go from A to P, and we're losing energy to the surroundings. So we say our delta H is negative, our enthalpy, and that's an exothermic process. So again, thermodynamics are path independent. I don't care how we get from A to P. The fact that we lose energy to the surroundings going to P, that dictates thermodynamics. Kinetics is path dependent, all right? How long does it take to get from A to P? Okay, and the way we can affect the rate, we've just seen up here through the Arrhenius equation, is by looking at the activation energy barrier and the temperature, all right? So typical curves will have this shape. And we go to a maximum point on this surface and that is called the transition state. It's where it's transitioning from A to B, and it's given the symbol TS, and for some reason they put this double dagger on there. All right, so let me erase the arrow here. I kind of messed this up, didn't I? TS double dagger. And that is the highest point on the potential energy curve. All right, that is where you are beginning to either break your bonds and start to form your bonds. All right, so the bonds are not complete. Therefore, it's going to have the highest energy, and it's called the transition state. Now, no matter whether a reaction is endothermic or exothermic, the transition state will always be the highest point on the curve. All right. So, the measurement from A to the transition state is the activation energy barrier. That's what affects kinetics. All right. So let me make this clear. EA is a kinetic parameter. All right. The bigger EA is, the slower your reaction goes. So how do I make EA bigger? All right. So let's look at two curves. A going to P. And A going to P again. All right. Actually, let me change the color of that. All right. So A going to P, we have our red transition state and our blue transition state. Just having trouble getting in the corner here. Here we go. Which reaction is faster? The one that goes through the red transition state. Which reaction is slower? The one that goes through the blue transition state. Which one's more exothermic? Neither, all right? They are, well, I don't know if it's neither. That's a trick question. They have the same what? They have the same delta H, all right? But they have different rates of reaction, okay? And that can all be seen through what we call the activation energy barrier, all right? So, like I said, even if the reaction is endothermic, my transition state will still be the highest point on the potential energy surface, all right? So no matter whether it's exothermic or endothermic, all right, the transition state's still going to be highest, all right? So measuring between A and P, that is my delta H, and in this case it's positive. Where's my activation energy barrier? That's measuring between A and the transition state, okay? So here, going back here, there's my delta H's, they're the same. There's my EA for that reaction. And there's my EA for that reaction. All right, so EA is measuring from the reactant to the transition state height. That's the activation energy barrier. And the enthalpy is the change between the reactant and the product, all right, the energy there. So to kind of fill in the axes there, E on the Y, reaction coordinate, which can be abbreviated R dot C dot, right? That's on the x-axis. So here, energy, R dot C. All right. Last thing we want to discuss is going to be something called reaction mechanisms. Right? So reactions typically occur through more than one step, right? There's some that do, in fact, occur in one step, but there are many that do not, all right? So let's look at a chemical reaction. Let's take NO2 gas and react it with carbon monoxide gas. And we're going to get nitrogen monoxide and CO2. All right. So this chemical reaction actually occurs in 2 steps, right? But you're just looking at this reaction here, and I said, this is it. You would just say, hey, that looks like 1 step. But that is what we call the net chemical equation. And this should sound familiar when you talked about net ionic equations in Chemistry 1. All right, it's almost the same idea here. So this is the net chemical equation. And it turns out that this reaction actually happens over 2 steps. Now, how do we know that? All right, well, much like rate laws, you can't look at the overall reaction and guess how many steps it occurs in. You have to study the kinetics of the reaction, i.e. the mechanism, how the reaction works, in order to develop the actual mechanism, and then you can tell how many steps that occurs in. All right, and we'll give an example from organic chemistry here in a moment. But let's look at those actual 2 steps. In the first step, the NO2 combines with another NO2 particle, and they combine to make NO3 and NO. So this is what we call step 1. Step 2, the NO3 produced from step 1 will react with carbon monoxide. And then it'll produce NO2 and CO2. Now, how do I know this? Well, it's in a book, to be honest, okay? But it's also been studied, right? And this is a well-known reaction. Did I know that by just looking at that previous net chemical equation? The answer is absolutely not, all right? That's not what we're getting into in this course. We're just talking about reactions that occur in more than 1 step, and what does that look like, all right? What we can do is we can add these 2 equations together, just like you would the ionic equations that you did in Chemistry 1, all right? If I look on the left side of step 1, anything that appears on the right side in step 2 will get canceled out, all right? So I have an NO2 here that will cancel out with an NO2 here, all right? All right, then on the left, I've got an NO3 here and an NO3 here. And anything that makes it through, just drop it on down. So we get NO2 plus CO gives us NO plus CO2. And this is what we call the overall equation, or overall reaction. Step 1 and step 2 are called elementary reactions. All right? They are steps that take place in the overall reaction, and they can be called elementary reactions. So when you add up all the elementary reactions, you end up getting something called the overall reaction, and accounting for each of the elementary reactions shows you what we call the reaction mechanism, all right? So let's break up some terms, or come up with some terms for that we see in reaction mechanisms, all right? So we'll look at types of elementary reactions. We can have A going to P, all right? This would be called a unimolecular reaction, because it only happened with A, all right? One single reactant resulted in a product. So that's called unimolecular reaction. And the neat thing about elementary reactions is, unlike overall reactions, we can look at their chemical syntax, if you will, and you can come up with the rate law. So in this case, the rate law for a unimolecular reaction of this makeup is going to be Ka. All right? It's first order in respect to A. How do I know that? Because you only have one A, all right? And it's an elementary reaction. There's nothing going on in the background. There's no funny business going on here. If you've got one A, it's first order respect to A, okay? Now, a different type of reaction we can look at is A plus A giving us P. This would be called bimolecular. And since it's an elementary reaction, there's no funny business going on in the background. Since I have two A's, it's second order in with respect to A. Okay? All you got to do is look at the number of A's, and that's your order. All right, very nice. You can have A plus B going to P. Now, this is also bimolecular. However, the rate law is going to be different. You don't have two A's this time. You have an A and a B. Okay? Now, in more advanced chemistry courses, what you would do when you study reaction mechanisms in kinetics is you'll start combining these rate laws and come up with the overall rate law for the reaction. Right? That's one way that they determine overall rate laws. Okay? If they know the mechanism, which means if they know every elementary step, they can combine the rate laws and come up with the overall rate law, which is pretty complicated stuff, but we're not doing that in here, so don't worry. All right?